This is a vector network analyzer. Its day job is measuring cables, filters, and amplifiers. You probably do not own one, but if you are a student, your university RF lab does, and one afternoon on it is enough. So here's the build. One antenna, one metal plate, and one question. Can an instrument see something move across the room? First, what the instrument does. Inside the box, a source makes a tone. It splits it. One copy is kept as the reference, the other goes out port 1 through your device and back in port 2. The receiver compares the two. Put the two waves side by side. The returned one sits shifted along its cycle, that is phase, and the phasor shows how far it turned. It also came back smaller, that is magnitude, the bar on the right. Phase is where the radar hides. Now, the build. Unscrew the cable. Put a horn antenna on port 1, another on port 2, and stand them side by side, pointing the same way. Port 1 transmits, port 2 listens. Put a metal plate a meter distance out. The device under test is now the room. The air, the plate, the reflection off it, that is what the instrument is measuring. Same instrument, same S21, only the device under test changed. Set the source to 2.5 gigahertz. That is a 12 centimeter wavelength. Now slide the plate 6 centimeters back and watch the polar display. The phasor sweeps one whole circle. 6 centimeters of motion, 360 degrees of phase. Here's why. The wave goes out and comes back. So moving the plate 6 centimeters adds 12 centimeters of path. One whole wavelength. And one wavelength is one full turn of phase. So delta phi equals 4 pi delta r over lambda. 4 pi is 2 pi for the turn, times 2 for the round trip. Turn that around and it gets fun. If 6 centimeters is 360 degrees, then 1 degree is 167 microns. Move the plate less than a millimeter and the phasor still twitches. Now repeat the sweep and log the phase. A slow target draws a gentle ramp that wraps at 180 degrees. Walking speed gives a steeper ramp. A car is faster than you can sweep. The phase wraps between readings and the slope lies to you. That is aliasing, your sampling limit. Two things to know before you call this a radar. First, the phase repeats. Move the plate another half wavelength and you read exactly the same number again. 6 centimeters, 18, 30, one reading, many distances. Second, the antennas are not picky. Some signal leaks straight from transmit to receive. The rest bounces off the ceiling, the floor, the bench, and every other object in the room. All of it arrives together as one number. So honestly, what did we build? Something that knows that a thing moved, roughly how fast, and nothing at all about where. Real radars fix exactly this. 4 classic answers. Continuous wave. Hold one tone and read only Doppler. Speed, no range. FMCW. Sweep the frequency, and the echo returns as a delayed sweep. So the frequency gap gives you range and velocity together. Pulsed. Send a short burst and time the return. Range straight from time of flight. Pulse-Doppler. Stack many pulses, and every range cell also carries a velocity. The last dimension is space. Add more antennas, and the phase difference between them tells you which direction the echo came from. That is a phased array. It is the same comparison we just made by hand, run across frequency, across time, and across every element. Range, velocity, angle, a live map of everything moving in front of you. But it starts here. One known signal, one echo, one phase difference. Build that, then go read about the rest.